And that, there should be a bounce down example. There's like a bounce down. But we just that.
That's good. That's really good.
Yeah.
Great call.
Yeah, they got really famous. Sorry.
I was over the summer.
The features.
Okay, time to get started. I have a lot of content to cover today, so I'll not ask any question before I start the contents. I'll probably ask some questions at the end, but yeah, feel free to interrupt if you have questions. All right, so in the last class, we talked about linear regression. And we said that linear regression is different. I mean, in general, regression is different from classification. Yes.
Can you post these slides
This one. Right now?
at some point, I guess?
Yes. Right after this class, I'll do that. Yes. So, the difference between regression and classification problem is your y, in case of regression, is a continuous variable. And for a classification task, it's just a discrete label, which is finite. So for regression, we are trying to predict a continuous value for y, like stock market, like temperature of a day or something. Where is the sound coming from? Oh, yeah, it's gone. Anyway, here, because we are not deciding on a label, predicting whether we have a correct label and computing some error based on that is not feasible, because there are the continuous numbers have so many possibilities that it's very hard to get it right. So instead of doing that, what we talked about was least square estimators, where we are basically trying to learn a function that maps x to y, and then we will look at the square difference between our prediction and the actual value. That's the goal. Rather than minimizing the classification error, here we are trying to minimize the least square difference, right? Now the question is, what is our f? And because we are talking about linear regression in this class, we'll go to non-linearity after midterm. But because we are talking about linear, so we are essentially talking about some kind of dot product, linear combinations, right? And that's why if we have a univariate case, you could see that to transform a x to y, a linear function is something like this. Function of x equals to beta 1 plus beta 2x, right? Which is exactly like a line, right? If you have a particular x, so this is like an intercept, and this is like a slope of that line. What happens when we have more than one variable? So then your x becomes a vector, and then your beta also becomes a vector, right? I mean, if you keep this constant apart, this beta becomes a vector. And we have previously seen that you can actually pack all the betas into one augmented representation. So what happens is you have function of x is equal to x beta, where your x is kind of x1, x2, dot dot xp, and your beta is like beta 1, beta 2, beta p, right? And if we do a multiplication of this, I mean a dot product, x1 times beta 1, x2 times beta 2, plus plus, dot dot dot, xp times beta p, we should get an estimate of y, which is y hat, right? And then you take a difference between y and y hat, and they're squared, try to minimize this. That's the goal. The reason function of x looks like this, because we are talking about linear regression here. Any questions so far? I was not supposed to ask questions, but anyway. Good. Okay, so now let's talk about this problem. So overall, we are given a training set, right? And in a training set, you have multiple training examples. Now you want to minimize the squared difference of the prediction and the actual number for all the training samples, not just for one example, for all of them. And you want to minimize the average of the least square error, right? So you are summing over all the examples in your data set and looking at the difference between your prediction and the original value squared divided by n, the average, right? And if we assume that f of xi is a linear function of x, then we could say this problem is similar to this x beta, actually xi beta, because there is I index, I beta minus yi whole square, right? Because we just said our function of xi is essentially xi beta, so whatever function minimizes this squared error now boils down to whatever beta actually minimizes this error. Question? It's just the linear function replacement. Okay. Now can we get rid of this term? So we are trying to do minimization of a function. What kind of beta will minimize this function? Does this matter? Why not?
Because with or with it, it's still going to be the same beta is going to be the minimum.
Whatever beta is doesn't impact this 1 by n. It's a constant. So in a minimization problem, I mean, differentiation of a constant is always 0. So it doesn't matter. So we can get rid of this thing. So essentially, we are trying to minimize this function. Okay? So now, this is a sum over all the possible examples in your data set, right? So you can write this in an alternative matrix formulation, where you don't need to go over the sum. The matrix multiplications will care about this sum. It's just a compact notation. What you can do is, you can define a matrix called A, which is essentially a combination of, a concatenation of all your training examples, where each x is essentially x11, x1 2 till x1p, like this, so on. So if we do, and then y the same way, right? Y is a vector of all the y1, y2 till yn. If we do this, then we can further simplify this function as this. So a beta minus y whole square, right? Because there is a whole square. But in a matrix format, what we do is a transpose and the original matrix, right? So squares in matrices are essentially written like this. This is essentially a beta minus y squared. Questions? Good. So now our problem has become, so here the beta hat, the beta star that we want to find, the optimal beta is essentially the beta that minimizes this squared matrix, this matrix multiplication. Okay. So get rid of this and we can just stick to this part. We'll now resort to matrix representation, and that's where your previous course on linear algebra will help. How many of you have gone through linear algebra course? How many of you never know like what a linear algebra is? What about others? Is there anyone who doesn't know what linear algebra is? Good, because you are supposed to know this. This is a prerequisite. Good. Now, so we are going to use like formulas from linear algebra to actually further simplify this problem. Okay? So let me go over some math now. So the function that we are trying to minimize is essentially this, times minus y, right? This is our function, this function, same function. This is what we want to minimize with respect to beta, because we don't know beta and we are doing linear regression. So what do we do? First of all, we will try to apply some matrix formula. We'll try to leverage, and we'll go back to the cheat sheet kind of thing that we learned from our linear algebra class and some calculus class, right? So we will first try to decompose this, which is essentially, there is no direct formula here that talks about this, but the whole idea is A plus B transpose is essentially A transpose plus B transpose. You remember this? Or if it's a minus, it's just a minus, right? So we are going to use this formula here. So what we are going to do is A beta transpose minus Y transpose A beta minus Y. Clear? Okay. Next, we are going to use for this one the top formula, AB transpose is essentially B transpose A transpose. So we break this to B transpose, beta transpose, A transpose minus Y transpose. Okay? A beta minus Y. Okay? Now we'll do multiplication now because we can just multiply between these two terms. The first one, beta T, A transpose, A beta. The second term, beta transpose, A transpose, Y. The third term, Y transpose, A beta. And the fourth term is Y transpose Y. Just multiplying. Okay? So next, look at the second rule. What it is basically saying is if you apply transpose on a multiplication of matrices, you can reverse their order with the transpose, the second formula. So that's what we are going to apply here. What that means is, this is the same term. So using the second formula, we'll reverse the problem, yt A beta, right? Minus yt A beta plus Y transpose Y. We just applied the second formula. But after we apply this, the good thing is this and this are the same term. So we can just write it like 2 of this. Okay? All right? So now, we still want to minimize this function, right? This is the function we wanted to minimize. So now, this is something we want to minimize. And what we do when we want to minimize? Take derivative, set derivative to 0, right? So take derivative of j of beta with respect to beta. So d beta, right? So now let's go back to our calculus class with matrix and vector derivatives, and we can see this formula. So xt bx, if we take a derivative of this, you get 2bx. So whatever is in the 2, whatever is in the middle, and then the matrix that is on both sides, right? So this looks like the same problem, right? We are taking a derivative of this term first. So we'll apply that formula, and that basically gives us 2, whatever is in the middle, and this is in the middle, and whatever on the other side, so beta, right? So just applying that formula. What about this? What is the derivative of this term with respect to beta? What is the derivative of the second term with respect to beta? We are taking a derivative of this term.
A beta.
Why 4?
Divided by 2.
Is there a 2 here? Because you are taking it, so this 2 is already there, but for this term, YTA beta, if you take a derivative, just think about forget metrics, just think about variables. What is the derivative of this function with respect to beta? YTA, right? This is the constant term in front of it. So 2 YTA. So minus 2 YTA. What is the derivative of this function, this term? 0. There is no beta. Good. So this is what the derivative looks like for this function, right? Now we have to set it to 0, right? To find out our solution that will minimize the function. And if we set it to 0, this essentially means ATA beta is equal to YTA, right? Getting rid of the 2 on both sides. And then beta is essentially, did I make any mistake here? YTA. Okay, not necessarily, that's fine, but they have a slight reformulation of this. So this function can also be written as ATY. I mean, we are just flipping the order, right? It's still the same dot product. Yeah. So now, so beta is equals to, if we try to take an inverse of this matrix, a inverse of ATA beta is essentially ATA inverse AT and Y. So we are essentially taking an inverse of this matrix on both sides, multiplying. So what happens to the matrix inverse multiplied with the same matrix? It's an identity matrix, right? So this is cancelled.
You just realize those should be canceled?
What?
Can't you just realize that the same terms can be removed?
You mean how, like A of t and A of t? Yes, I'm coming to that. That's a good question. Yes, let's come to that part. Yes, that's a good question. The question is, why do I even bother this? Rather, I could do something like this, because the question is, what I could do is, I could just say, because this is equal to this, I could just cancel AT transpose from both sides, right? And then I could take A on this side, which is essentially multiplying with A inverse. This is the question, why we are not doing this. Anybody? Why not we are doing this? What is wrong with doing this?
Is it because you're left with an A inverse? I guess-
What is the problem with A inverse? What?
I don't know.
What can be a problem with A inverse? Yes.
There might not be an inverse of it.
It might not be invertible. What is the condition for a matrix to be invertible? What is the first condition you have to satisfy?
The determinant cannot be 0.
Even before that,
Square.
it has to be a square matrix. What is A? Remember, A is your matrix of x's. Right? It's essentially x11, x12, tx1p, x21, x22, x2p, and so on. Is it a square matrix? Very unlikely, right? Because the dimension p and n are very less likely to be the same. So even like if we want to do this, we don't have a square matrix in our hand in the first place. Now, ATA, is that a square matrix?
Yes.
Yes. It is always a square matrix by definition. Because if A is, let's say, n cross P, AT will be P cross n. So it will be P cross P, square matrix. Right? So that's the reason we don't want to simplify like this, because this is not invertible. Most likely. All right. Any questions so far? So instead of doing this, what we want to do is this. ATA inverse, which is more likely to be invertible. It's not guaranteed. Right? Why it's not guaranteed? Why is it not guaranteed?
Because we've only established one part of figuring out that it can be invertible. We still don't know if like the determinant.
Right. So that's the first condition. Like it has to be a square matrix, but the determinant of this matrix also has to be non-zero. And we don't know that. Still, it's possible that this is not invertible. But if it is, then we are done. This is the beta that actually minimizes. This is the beta star. And why it minimizes? We can still take a second derivative and see that the second derivative is positive. That will tell us this is actually minimizing, not maximizing. Take a derivative of this function. What happens? What is the derivative of this function?
2A transpose A.
Yeah. 2A transpose A. What is the derivative of this function? This term, sorry, 0. So if we set it to 0, sorry, we don't have to set it to 0. This is just a second derivative, right? So, and what is this matrix?
It's like the square.
It's a squared matrix. So that's why it's a positive semi-definite. So it's positive, so this is minimizing. Right? Life is good. But then the question is if this is invertible. Even if this is invertible, matrix computations are costly. Right? It takes time. So not often we want to do this. What is our other alternative? Because we have two problems. One is it may not be invertible. Even if it is invertible, it may not be very computationally efficient. What else we can do? We have a minimization problem in hand, yes.
Numerical methods like gradient or whatever.
Exactly. So we can go to numerical techniques, gradient-based approaches to do some kind of gradient descent, right? Because we are doing a minimization problem here. Right. So we will do gradient descent exactly In what direction?
Down. Or minimizing.
Yes, we are minimizing, so beta should be updated in this direction. Right? This is the derivative. This is the gradient. Right? So, we should be, our formula for beta t plus 1 should be equals to beta t minus a learning rate of alpha by 2, and I will explain why by 2. Don't worry. This term, 2 ATA beta minus 2 YT. I mean, YTA and ATY are the same thing. So just to be consistent, because we have AT here, ATY. Now you will see why this 2 is here, right? Why?
It cancels it.
We can cancel them out. It doesn't matter actually, because we have this alpha to control. Whatever we set alpha, that will do our job. It's just a mathematical notation thing. We have the complete freedom to choose alpha. It doesn't matter. It's just a step size we are changing. And we can change the step size as we want. So beta, and here is a minus. Why is this minus? Because we are doing descent, not ascent. We're doing gradient descent. We're doing minimization. So this is the final formula. The good thing here is now we already know this. We start with some value. This is known. This is a just matrix multiplication, and this is another multiplication. There is no inverse or something. Right? Yes.
I got confused about what matrix A is. That's the matrix of the X.
All the yes. So X A is the row matrix. A is the so A is a matrix where each row is X. Right? And Y is just a vector of Y1 to Yn. No question? Very good. That's our solution, the gradient descent solution for linear regression. So we have learned 2 ways. One is the closed form formula that takes the inverse, matrix inverse. And the other one is gradient descent. And you can also do gradient descent in a stochastic fashion. So rather than looking at the entire matrix, you could look at one example and make some update to the beta. And you can keep doing it and it will still converge. It is called a stochastic version of the gradient descent. Okay? So this is the batch style formula, but you can also do it in an online fashion. All right. Good. And again, for the step size, we have the same plot here, right? I mean, what should be our alpha? And then if you have a too large alpha, you will like keep jumping around the optima without reaching it. And if you have a too small one, you will need a long time. So you want to pick an alpha that optimizes the time as well as your global minima. Okay? We have seen this before. So now the question is, remember in logistic regression, we didn't talk about least square. We talked about what? Here we are minimizing the square difference. But in case of logistic regression, what did we try to do? Did we try to minimize or maximize? Maximize. Maximize what?
The weight.
Weight. The The likelihood, yes. So there we are doing maximizing likelihood, and here we are minimizing least square. Question is why? Anybody? Yes.
The first one is probability or likelihood of success, which is good. And the second one, we're minimizing error or how wrong we are. So that's
Okay. So you are saying basically they are different problems, so we have different approaches to them. Anybody else?
We're trying to fit a prediction line for the values of the data instead of like classifying one side or the other.
Okay, for the sake of time, the answer is they are essentially the same thing. Minimizing least square error is essentially maximizing likelihood of the data. But there, the likelihood was get a data and its label, how likely they are to appear together. Here, given the data, how likely you are going to see this exact value of y. It's just the definition of likelihood is different, but it is exactly the same as maximizing likelihood. And this is what this proves. So let's prove this. Let's prove this. That minimizing least square is exactly maximizing the likelihood of the data. But in case of linear regression, we have to make one additional assumption. And here is it. The assumption is, remember we had y hat as x beta, right? This is what our linear regression problem is, right? Clear? So is y hat always going to be equal to y? No. Essentially, like maybe there are multiple reasons why it may not be. Maybe our beta is not right. Maybe y, the real value, has some noise associated with it. We just don't know. So essentially, we can write the difference between y and y hat, if we call it epsilon, then we can essentially say y is essentially x beta plus epsilon. And if we assume that this is just random noise that's coming from the observation, then this epsilon, we can assume that it follows a Gaussian distribution with zero mean. Okay? That's what it says. So it follows a Gaussian distribution with zero mean and sigma square variance. Okay? If we make this assumption, then we can show that minimizing the least square is essentially maximizing the likelihood of the data. Under this assumption that the data you are actually seeing, the errors that are being made by your model is essentially because the real data you have sampled have some random noise, which follows a Gaussian distribution. Okay? So how to do it? So remember, the maximum likelihood estimate of beta is essentially what? Probability that you will see all the xi combinations given some beta, some sigma square, and that's it. I hope so. Yeah. Yeah. And you will see all the x's. So it's basically x1 to 1 and so xn yn given this, right? But previously we said this is a sparse problem. Yes.
Is the identity matrix within the standard deviation, is that because like it's a multidimensional normal distribution for the epsilon?
It's because it is essentially saying you have an if you multiply this, essentially sigma square I is essentially multiplying with a identity matrix, right? So it's basically saying your diagonal has the values. There is no covariance like in the non-diagonal elements,
Okay.
right? So whenever you are going to add a noise, that is going to be along the diagonal.
That makes sense.
Okay?
That makes sense.
Yeah. All right. Now, because this is a sparse problem, like seeing this exact data set, the exact number of example is going to sparse. What we do? What is our trick? We make an assumption. What is that?
The
Independence of what? What was the name? ID. Right? We make the IID assumption. And that basically tells us instead of all the examples joined together, we can just multiply this probability over I. Because each example is independent of each other. And they have an equal probability of being sampled. If we make this assumption, life gets a little easier. Now, there is just one set of xi and yi here, and multiplication over them. Okay? And because this is a multiplication over a lot of terms, we did a log of this thing. We took a log previously, right? These are things we already know, right? We took a log, and which became a sum over log of probability of xi, yi given beta sigma square. But here is the thing. Xi does not depend on anything. It's our data sample. Our function is this. Y is dependent on x and beta, but x doesn't depend on anything. So rather y depends on this. So we can convert this into a conditional probability of yi given xi, beta, and sigma square, because x is independent. It is essentially the same problem. And we don't need to worry about log, because we are essentially trying to maximize the function. Whatever, if I try to maximize a function of x, that is equivalent to maximizing the function of log of x. Log doesn't transform the optimal solution for a function, right? I mean, whatever function you have, if you optimize for it, and if you take a log of that function and optimize for it, it will be the same solution. So the order of the function is not changed. But what is this? This is essentially this. Probability of y, we have assumed that this follows this function where this is a linear transformation, but this part is essentially a Gaussian distribution. That means y is a Gaussian random variable which follows a normal distribution with a mean of x beta and a variance of this. Right? Because this is the mean. All we are doing is adding random noise here, which is actually distributed according to the normal distribution. So essentially, y is nothing but a normally distributed variable with x beta as mean and sigma square as the standard deviation. Is this clear? So if a variable follows this, we can plug in the probability of Gaussian random variables, right? So probability of yi given xi, beta and sigma square will be this bell curve. And the definition of that is sigma root over 2 pi e to the power minus half yi minus the mean divided by sigma whole square. I mean, this is the definition of a Gaussian distribution. This is the variance, this is the mean, and this is the observation, the difference squared, e to the power that, and there is some constant term. So if we now plug in this formula here, what we are trying to do is this. 1 divided by sigma root over 2 pi e to the power minus half yi minus x beta divided by sigma whole square. Okay? Now, in order to minimize, find the optimal beta, what terms can we get rid of from here? Can we get rid of sigma?
No, we're.
Is beta dependent on, is this term dependent on beta?
We can't get it.
We can. Can we get rid of this? Yes. So this is a constant term we can get rid of. And again, this is a e to the power function, and we have said adding or removing log doesn't make any difference. Let's plug in the log again. Doesn't matter. What we get? If we do that, log e to the power, this cancels, and all that remains is this term, which is essentially a minus over I half, 2 sigma square yi minus x beta whole square. Right? Can we get rid of this? 1 by 2 sigma square? It doesn't depend on beta. Get rid of this. So, maximizing the likelihood has gone to, see the minus, minimizing the least square under this assumption. This is the assumption. Questions? In logistic regression, we didn't have to make this assumption because y was just a discrete label. But here y is a continuous function of x, and that's why there will be, we can never, it's very impractical to match the exact value, so that's why we model this as a sum of some random noise, which is very intuitive. And if we assume that this follows a Gaussian distribution that looks something like centered around 0 with a variance, standard deviation of sigma, then the distribution of y looks like this. Looks like this. And maximizing this is essentially minimizing this. Clear? Good. Okay, now we come to the last part. Which is called regularization. Think about this problem again. Now we have learned how to find a beta that can do this transformation. How to find a beta that can transform x to y, right? Linear function. How many betas are possible? Are we going to have a unique solution? Yes.
For maximizing likelihood, minimizing for that problem, I think it's likely there's a unique solution.
Sorry, what?
I think it's likely there's a unique solution.
Yes, but
It's not like given.
if we do the matrix inverse and there is a inverse that is possible, right?
Right.
Right. But often and then we are not interested in that unique solution, or we are doing gradient descent. There are multiple other solutions that might still work fine. Or maybe the unique solution is not the solution I am looking for. I have a particular preference for the solution. Well, what do you do? Let's say I like a particular kind of beta. I have a preference. What can we do?
Impose a prior.
Impose a prior, exactly. If you say, I like a beta that follows a Gaussian distribution, right? We could impose that prior. And then this function, I mean the beta we will learn will try to obey that constraint. In other words, this optimization problem will be regularized by our prior, our preference. And it is often very important. For example, maybe X is very high dimensional, let's say 1000 dimension. Now, if I learn a beta, I need to learn a beta that is 1000 dimension in order to do the dot product, right? But then if I want to interpret this beta, interpreting 1000 different numbers is hard. Probably I want to focus on the most important features. I don't want to give weights to all the features. I just want to find the main 10 features. That means even if the optimal solution, the unique solution I'm going to have, that may have all 1000 different components of beta to some value set, which I don't want. So in other words, I want to regularize this optimization problem as I see fit. What serves my application need better. Okay? So the way we do it, we impose prior. Exactly. So the first prior we are going to talk about is the Gaussian prior. So first prior we are going to talk about is Gaussian prior. Here we are assuming that beta follows a distribution like this. Then how does our our optimization problem changes, right? That's the question. So if you look at the solution, is essentially now we have, instead of, because we are adding a prior, we don't have a maximum likelihood problem, we have a maximum a posterior solution, right? Because remember, probability of y given x is proportional to probability of x given y, probability of y, right? Bayesian. What did we call this term? What is this?
A posterior.
Is it the posterior? This is the likelihood. This is your data, x. This is the likelihood. What is this? Prior. What is this? Posterior. Yes. Because instead of maximizing the likelihood of the data, we are going to now maximize the joint probability of the likelihood and the prior, because that's what we are going to impose. And that's why this is a maximum a posterior problem formulation. The solution we are going to get is a maximum a posterior solution, not the likelihood only. We are adding this, we are multiplying this probability, right? So, is essentially the first term that we had. So we are going to take an argmax of beta that maximizes the log likelihood, probability of xi, yi, for I equals to 1, 2, okay. So this is how they are writing this. Probability this term with this I equals to 1 to n given beta and sigma square plus log of probability of beta. So just this is the previous likelihood formula. There is nothing new here. It's just the probability that you will see this data combination, right, given this value, but you are just adding another term of log, multiplying in the real domain is essentially doing an addition in the log domain, so log probability of beta. This is the general formula that we will have to follow whenever we are imposing some prior to do regularization. And now we are going to consider two different cases. This is exactly the before as the likelihood function. This part is where we will consider two cases. One is the Gaussian prior, and the other one is the Laplace prior. Okay? And this is how it is written. So beta follows, and we have a different parameter tau here, just to distinguish from the sigma in the likelihood function, and we have another standard deviation term here, tau, for the prior, which is different from the likelihood one. Okay? So if we go back to the Gaussian distribution definition, the definition is probability of beta is equals to root over 2. I just don't want to do a mistake here. What is this? Sigma root over 2 pi. Sigma root over 2 pi. And here there is no sigma because it follows the tau, right? So it has to be tau for the prior. And then what you do is e to the power minus half beta minus 0 divided by tau whole square. Why 0? Why beta minus 0 here? Okay, normally in a Gaussian distribution, what this term should be? What is the definition of Gaussian distribution? What goes here? The mean. The mean mu goes here. But the mean is assumed to be what? 0. So get rid of it. Right? Now, if we want to maximize this, we just want to take a derivative with respect to what? Beta. And for this part, because we have already solved the first part, likelihood, already, we just need to solve for this part. So for taking a derivative with respect to beta, what can we get rid of? Can we get rid of this?
Yes.
Why? There is no beta. Good. And we said whenever we are in trouble, we can ask help from log. He's a good friend. And then log and e cancels out. Right? And then what you have is minus beta square by tau whole square. Right? Which is essentially minus 1 by 2 tau square beta square. What can we get rid of from here to optimize for beta?
So 1/2 for the sphere when you do the chain rule.
1/2.
So you'll multiply, when you take the derivative, you multiply by 2, and then it'll convert to 1.
Yeah. Can we get rid of this?
I think that stays, doesn't it?
Yes. But think about the beta optimal. Does it matter if we keep it or not? It doesn't matter. Right? So we can get rid of this. So essentially what remains is this, which is essentially minimizing the L2 norm. If we assume Gaussian prior, this is called ridge regression. So previously we only did optimize for the least square, which was y minus x beta, right? Whole square. We minimize this. But now we also want to minimize for beta square itself as well. So this becomes our final optimization function. Yes?
Would ridge regression do something like you were saying about it caring about fewer values? Or
No.
No, okay, let's make sure.
No. No.
Then what's the possible use of ridge regression? Like, why do you want to minimize b? Or why do you want to make b closer to 0?
Because you may want your beta to be to have a certain radius, the absolute value of beta, you may want it to be not larger than within a circle. When you want that, the way you enforce that is through Euclidean distance. So if we force that this beta square should be minimized, then it will try to find the smallest circle that actually has the optimal beta. Okay? It may not have sparse solution, but it will have a lower magnitude solution. That's why when you want to, if you care about that, that's when you want to do ridge regression. Rather, a solution may be somewhere here rather than here. Because your linear function is like this. So what it will try to do is to write this kind of circles. And here will be the optimal point that intersect between the two. And that is not going to be sparse because you still have something in component here and some component here. And in terms of a solution, here if you take a derivative, sorry, I didn't take the derivative here, right? So it has to be 2 beta. If you take the derivative, that's the direction you should go. But essentially you are trying to minimize this. This is what we are trying to minimize. This is the direction you want to go. Right? Okay, the last part, the Laplace prior. So the Laplace prior is defined like this. So your beta follows a Laplace distribution 0 and t. And the Laplace formula is defined as, the whole formula is not here, but I can write from here. Probability of beta given Laplace distribution has 2 parameters, mu and b is equals to 1 divided by 2b e to the power minus beta minus mu divided by b. This is the definition of Laplace distribution. It has 2 parameters. One, mu is the mean. Okay? But here, if we assume a 0 mean and a standard deviation of t, then this mu is gone. It's just the b by itself. Okay? Now you want to optimize for this, you take a derivative of this, right? Yeah. So first of all, if you want to optimize for the beta hat, this term doesn't have beta, you get rid of it. This doesn't have beta, get rid of it. All you have is this. And your friend is again here to save you. So you get rid of this. So all you have to do is to take the derivative so your probability still, your probability of this is this function. So you are essentially minimizing for the L1 norm now instead of the L2 norm. But to find this, we need to take a derivative of this, right? The actual derivative, because in the first case we had the beta square, the derivative of which is 2 beta, which was easy. But here it's not possible. So there are extra tricks to approximate some kind of derivative, but I am not going there today. But the whole point is, if you apply this constraint that your solution follows this Laplace distribution, it essentially boils down to minimizing the least square x beta minus y whole square plus the L1 norm with Laplace. With Gaussian, it becomes the L2 norm squared. So again, coming back to Laplace, it is essentially your L1 norm, and this part, how to optimize this, is not going to be covered in this class. We'll see this sometimes in the future. But the point is, there is no closed form solution for computing a derivative of what is this called? Absolute value function, right? Yes. And this is called lasso regression. So lasso regression is maximum a posterior least square regression with the Laplace prior. And ridge regression is the same problem with the Gaussian prior. And these two are popular regularization techniques that are used widely in machine learning, because sometimes we want solutions to be within a particular circle. We don't want to consider a solution that is far away. We want to define a smaller solution space. Or sometimes we want a sparse solution. How to do that? So think about this modular term, this function. So in case of square, in case of L2 norm, it was a circle. But L1 norm looks like a rectangle. Right? So essentially, let's say you have this rectangle for L1 norm, and you are trying to find out a common solution that satisfies this and this. And this is a line, right? Plane. So maybe the plane will hit you somewhere here. So this will be the solution. Right? Optimal solution. So here you see, if this is beta 1, if this is beta 2, beta 1 is equals to 0 here because of this nature of this function. And that's what happens. So L1 norm is essentially looks like this. L2 norm looks like a circle. L3 norm looks like an oval kind of thing. L4 norm looks like even another oval. And if you go to L infinity, that will look like a rectangle. Any solution within that rectangle is a feasible solution. But the reason L1 norm is popular and the lasso regression is popular because it kind of forces your solution to be sparse. When you want many, many zeros in the W vector or the beta vector, and only a few of them to be non-zero. So that concludes today's lecture, but there are some announcements. First of all, in the next class, I was supposed to teach regularization, but I kind of like did a express lecture today to finish that. So the TAs will be coming in the next lecture, and I'm actually traveling to Atlanta for a visa interview, so I cannot be in the next class. So the solution, I mean, in the next 2 classes, we will discuss the solutions of the 5 assignments you have gone through. And we'll divide it into 2 classes, and we'll take more time discussing what kind of questions can come in the midterm. Okay? So in the next class, you will see the TAs, and also after the next class, you will see the TAs. Then after that, you have the exam. After that, you have the exam review. Okay? After that, it starts with the presentation. And we will very soon post your schedule for presentation, who is presenting on what day. The presentations will happen right here. And we will give you slots of 15 minutes around where you come and discuss your progress. So if you haven't started on your project, high time, start your project. All right? Thank you. See you after midterm.
మనోడు ఉంటాడు అక్క తింటమే బిస్కెట్